In this video, I want to talk about computing the forward pass in a neural network. So by the forward pass, I mean plugging in a single input, in this case, and computing the cost. So let's define the cost, and let's also define the activation function. So the activation function would be our sigmoid function, and the cost will just define as the difference between the z's, the output units, and the y in the Euclidean distance sense. So we'll compute cost, and it's going to be a function of the y and also of the z, which we'll call net w of x. So z is net w of x. Why is that? Well, because in order to compute the z, what you need to do is you need to plug in the x into the network and get the z's. Hence, net w of x. And of course, if w changes, well, the z's change as well. And what we'll do is we'll just compute the Euclidean distance, the squared Euclidean distance between those. So it's going to be the sum over j of yj minus net w x j all squared. So that's going to be like that. And how do I compute this kind of unit? So let's say that you want to compute h13. So h13, for example, is going to look kind of like that. So we'll compute h13 by saying that what we want is we want to compute the sigmoid, so the activation function, of a linear combination of the inputs. So what are the inputs to h13? Well, as usual, what we'll do is we'll define the weight here as w in the first layer, going from this 4, and going to h13, going to this 3. So it's going to be the sum, again, over j of w all in the first layer, starting from j and going to 3, times xj. We also need to add the bias. The bias is associated with this unit, and it doesn't care about the axis. It only cares that it's associated with this unit and that it's in this layer, so we'll denote it as B13, like so. So the reason there is a j here and there's just 3 here is that there's lots of weights that are associated with this hidden unit, but just a single bias. So we just omit the j because we just have the one b, whereas we have lots of w's. So the formulas for the h's in this layer and the z's are going to be similar, so we can just compute that. Now, as we mentioned, this is a computation that can actually be vectorized. How would you vectorize this computation? Well, you would say, let's say that I don't just want to compute the one h13, I want to compute h11 and h12 and h13 and h14 all together. How to accomplish that? Well, what we need to do is we need to set up a computation whose result is this vector for every number, not just the 3. So what would that look like? Well, the vector would look kind of like that. It will be the sum over j, w1j1 xj plus b11. And then here you'll have the sum over j of w1j2 xj plus b12, and so on, after which point you can apply the sigma. And that way, what you'll get is a vector that consists of all of the h's here. Now, the observation that you can make next, so here we'll have a closed bracket and a closed bracket. So the observation that you make next is, oh, this looks a whole lot like matrix multiplication. Because what you're doing here is you're saying, well, if I had a matrix where the W1J1s were its first row, and the W1J2 were its second row, and so on, and I multiply it by x, what I would get is this kind of thing. So what we do is exactly that. We set up that matrix. So that matrix would look like this. So what we'll do is we'll just say, okay, so the first row is all of those guys. So it would be W1, 1, 1, and then the second element here would be W1, 2, 1, and so on. And in the second row, what we'd have is this kind of thing. So 1, 1, 2, and W1, 2, 2, and so on. So if we set up a matrix that's like that, and if we multiply it by x1, x2, and so on, what we'll get is this part. If we then add the b, so let us do that. So we'll add b1, we multiply all that, and we apply the sigma. What we'll get is that this is the same as this. All right, so all that's left is to set up the matrix that's like that. And once you set it up, you can compute all the h's all at once. You can similarly compute all the h's here and all the z's here.